Chapter 7 is concerned with energy and chemical processes. We begin Chapter 7 by discussing what we mean by energy and also the units that are used to measure the amount of energy. So energy is defined as the ability to do work. Essentially, the more energy a system has, the more work it can do. The SI unit for energy is the joule, and we give the joule the abbreviation uppercase J because it's named after a person. It can be useful to define what we mean by work to help us understand a little better about what we mean by energy's ability to do work. Technically, work is defined as moving an object against a force. So, for example, when you lift a weight against the force of gravity, you're doing work, and that requires energy. In chemical systems, the force that we're often working against is the force of the chemical bonds that holds together atoms in compounds. Commonly, and your book loves to use this unit, the non-SI unit, the calorie, is used to describe energy changes. The calorie is defined as the energy required to heat 1 gram of water 1 degree Celsius. Now, it's a little bit confusing because it turns out that there's actually 2 types of calories. The calorie that we're talking about has the abbreviation lowercase c. However, there is also another calorie, sometimes referred to as the nutritional calorie, that has abbreviation uppercase C, and that's often used to describe the energy content of foods. But it's interesting to note that this is actually a kilocalorie. So you've got to be really careful using calories to take note of whether they're abbreviating it with a lowercase c or with an uppercase c. And it can get confusing. You can see this label here it's really unclear what's going on with the energy content here. They've abbreviated calories in a non-standard way, and then they've used an uppercase K where they should have used a lowercase k for the prefix kilo. So I don't like using the calorie because it can get messy. However, your book seems to have a habit of using it quite frequently. So energy is related to heat and temperature. And in particular, what we should realize is that heat is a form of energy. Heat is the energy associated with the random movement of particles in a sample of matter. And we should recognize that the energy will spontaneously move as heat transfer, which we abbreviate with the letter lowercase q, from a hotter object to a cooler object. So it always goes from the hot thing to the cool thing, warming up the cooler thing and cooling down the hotter thing. So if you have a glass of water, you put some ice cubes in it, what will happen is that heat will move from the water into the ice. And if you transfer enough heat out of the water, you might eventually melt the ice. So heat transfer, the transfer of energy in the form of heat, will change an object's temperature, and if you transfer enough energy as heat, it'll change the physical state of a substance. The heat absorbed or emitted by an object is directly related to its change in temperature. So what we're really saying here is that the more heat that you transfer, the bigger the change in temperature you get. That's what it means when 2 things are directly related. Similarly, we note that the greater the mass of an object, the more heat it takes to change its temperature. That is, for a given temperature change, as the mass goes up, the amount of heat that you will need to transfer to change the temperature of that object will also increase. The specific heat capacity, which we've seen in the lab, often abbreviated as lowercase c subscript s, is the amount of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. Every substance has its own unique specific heat capacity, so it's often a property that is used to identify a substance. And in your book, you have a table of specific heat capacities if you should need them when it comes time to solve some problems. So, as we've already observed in the lab, the relationship between heat, mass, and temperature change, along with the specific heat capacity, is given by this formula. Q equals the specific heat times by the mass of our object times by its change in temperature. I should point out that when we're calculating the change in a quantity, we always do so by taking the final value of that quantity taking the final value and then subtracting the initial value of that quantity. So this is an example from the book. It says what quantity of heat, so we're trying to find Q, is transferred when a 150 gram block, so M equals 150 grams, of metal is heated from, so our initial temperature is 25 degrees Celsius to 73.3 degrees Celsius, so that's our final temperature. And what is the direction of heat flow? So let's do the first bit and get Q. In order to get Q, we need three things. Q equals mc delta T. So it looks like the only thing that we're missing is what C is. So let's see if we can find it. And we're told that this is a block of iron metal. So can we find iron in here? Here it is, iron. And its heat capacity over here. I want to pay attention to the units. There we go. So C equals 0.108 calories per gram per degree Celsius. So let's go ahead and calculate Q now. Q equals our mass, 150 grams, times by our heat capacity, 0.108 calories per gram per degree Celsius. And then finally, we have to multiply that by the change in temperature, which is always our final temperature minus our initial temperature, and that's in degrees Celsius. So let's put all of that into the calculator. 150 times 0.108 times parentheses 73.3 minus 25, and then close the parentheses. Having done that, I end up with 782.46. So now let's check our units. We can see that grams will cancel and degrees Celsius will cancel. So the only unit left is calories. So let's think about our significant figures here. Looks like we've got 3 sig figs for our temperatures. And we've got 4 significant figures over here. This guy was 3 significant figures. So I would make this 3 significant figures in order to be correct. Now, we want to be a little bit careful, because when I look at this problem, I see something interesting. I see that there are 2 question marks. So that means that I've got more than one thing to answer, right? Always look for the question marks. So we've got 1 question mark there, and we've done that bit. Now it says, what is the direction of heat flow? So the temperature of our block of iron is increasing, so we can say that heat flows into the iron. Okay, heat flows into the iron. Okay, so not too bad. Here's another one. It says a 10.3 gram sample of a reddish brown metal. So mass equals 10.3 grams. It says gave off 71.7 calories of heat. So this word here is key. It says gave off, so that means that the heat was lost. So we want that to be negative for that reason. As its temperature decreased, so confirming that the heat was lost from 97.5 degrees Celsius, so that's where we started. T initial is 97.5 degrees Celsius to 22 degrees Celsius. So that's our final temperature, is 22 degrees Celsius. What is the specific heat of the metal? And can you identify the metal from the table? So again, we've got two things. We want to make sure we do the last thing that we need to do at the end. So let's see what we've got here. We want to try and figure out what the specific heat is. So I like to begin by writing out the formula. Q equals MCAT. And there we go. And then we want to solve for the specific heat. So this is very similar to what we did in the lab. So I'm going to divide both sides by M delta T. So Q on M delta T equals C. And when you put this into your calculator, make sure you put the bottom line in parentheses. So whenever you have multiple things in a fraction in either the top or the bottom line, go ahead and put that in parentheses. So I'm going to calculate the delta T in a separate calculation. So it's going to be my final minus my initial. So my delta T, 22 minus 97.5. And that gives me negative 75.5 degrees Celsius. But it's negative because the temperature is going down. So now Q was minus 71.7 calories divided by 10.3 grams times by negative 75.5 degrees Celsius, and that equals C. So therefore C equals, if we think about the units here, it's going to be calories over grams over degrees Celsius, which is exactly what we want because that's what we see in the table there. So let's see what that is. Negative 71.7 divide parentheses 10.3 times negative 75.5, and the number I got was 0.0922. 0.0922. Now, oh, there it is, look, copper. And that's nice because it's a reddish brown metal. So if you think about the copper pipes in your house and what color they are, you'd probably describe them as being reddish brown. So there we go. So we figured out what the metal was. It's probably copper. Okay. This is an interesting one. It says a 10.7 gram crystal of sodium chloride, so mass is 10.7 grams, had an initial temperature of 37 degrees Celsius, so T initial is 37 degrees Celsius. What is the final temperature? So T final equals what we're trying to find. If 147 calories of heat were supplied to it. So Q is positive 147 calories. So we're going to put the heat in. So I guess what we know is that that's going to make the temperature go up. So when we're finished with this, we would like to get a number that is bigger than 37. Now, what we need to do is go to our little table and get the heat capacity, the specific heat capacity for sodium chloride, which is 0.207 calories per gram per degree Celsius. So what I'm going to do is I'm going to do it like this, right? I know that Q equals mc delta T. So if I divide both sides by mc, I can get delta T, how much the temperature went up by. So let's go ahead and do that. So Q was 147 calories, M was 10.7 grams, and C was 0.207 calories per gram per degree Celsius. So that's equal to delta T. So delta T equals, let's do the math, 147. Now you want to make sure that you always put multiple things that appear in a fraction inside parentheses. So 147 divide parentheses 10.7 times 0.207. And so we're saying that the temperature goes up by 66.37 degrees Celsius. So our final temperature, if this is what it went up by, it's going to be pretty easy to calculate, isn't it? It's going to be where we started plus how much it went up by. So I'll just put that into my calculator. And then I'm going to round to the 0.1s. And there's my answer. I rounded to the 0.1s because my initial temperature was given to the 0.1s. And I'm adding numbers together, so my final answer should go out to the 0.1s. Okay, that one I would argue is a little more tricky. So that concludes the sections on energy and its units and heat and its relationship to temperature.